Hi everybody, this is Austin Hoggett here to give you another OpenStax Intermediate Algebra lecture, again here from Chapter 6. Today we're going to be utilizing all the general strategies of factoring that we've talked about in regard to polynomials. Generally, this is the best method to work out any of these quadratic problems that we're going to see, and they come in a couple of different varieties. You can see the tree branch here starts with the question of identifying a greatest common factor, and generally that's a good start for trying to figure out how to break apart some expression. We'll see today how that factoring technique, and there's plenty of them that you see here, is actually useful for solving a particular equation. Here's our learning objectives. We're going to talk about something called the zero product property. The zero product property is quite useful in using this sort of factoring techniques to identify the solutions to some type of equation. Now, we're going to stick mostly with quadratics. We'll also see some instances where we use the polynomial function notation to answer these questions as well. So let's look at a few examples. Let's describe first, though, what the zero product property states and get a sense of what the variety of questions might look like. Polynomial equations, generally speaking, are going to have more than just one variable, or rather an exponent greater than 1 in their expressions. And they usually are going to be put into a specific format. And you can see it down here. This quadratic form is put in this manner, and set equal to 0 is generally how we say this, so that we can apply certain techniques to it. We'll also learn later on something called the quadratic formula, which takes this generalized expression and solves it for x, no matter what the values of a, b, and c happen to be in our given situation. But you can see the variety of ways in which these types of problems can be presented. I've got 4 different varieties sitting in front of me here. And so there's lots of different ways this question could be presented. What we're going to talk about for the factoring techniques requires that we set all the problems equal to 0 before we begin. Okay, so let's look at a specific example of how the zero product property comes into play. The zero product property allows me to take my expression on the left-hand side, once I've set the equation equal to 0, and factor it into a and b. We're able to factor it using those techniques that we talked about before. And applying the zero product property tells me that if I multiply 2 things together and get 0, that means either one or both of those factors has to be equal to 0. So let's look at a specific case. Here I'm asked to solve 5n minus 2 multiplied by 6n minus 1 equals to 0. And generally, when we look at an equation like this, our instinct might be to FOIL this out. But in fact, that's not necessary. We can think of this as factor a multiplied by factor b equals to 0. According to the zero product rule, that then must mean that 5n minus 2 is equal to 0, or my other factor, 6n minus 1 is equal to 0. So with that in mind, I can actually now solve for each of those values with relative ease. Looking at the first equation, 5n minus 2 equals to 0, I just need to move my constant to the right-hand side of the equation, so we add 2. I'm left then with 5n equals to positive 2, and when dividing, I get my solution, or at least one of them, 2/5. That is one answer to this question. And so by the same sort of methodology, we can move our constants to the same side and solve in the second case, getting our second solution 1/6. N equals either 2/5 or 1/6 is the only way that the two sides of this equation are equivalent to one another. You might be surprised to get 2 different answers here, but we really shouldn't be. Initially speaking, I mentioned that we would try to avoid doing some type of multiplication here. But if I actually do the multiplication, in other words, if I FOIL this expression out, I get 5n times 6n is 30n squared. 5n minus 1 and then minus 2 times 6n should give me something like negative 22n and then plus 2 at the end. Okay, so take a look at this expression. I want to draw your attention to the fact that one of my terms happens to be squared. This goes back all the way to our discussion about the degree of a polynomial. In the context of an equation, the degree of this polynomial actually signifies to me how many solutions I should expect. With the degree of this polynomial being 2 and getting my 2 solutions here, that should check out. So those are the only 2 values that make this equation true, that set each side equal to 0. Applying that zero product property is just a way to take that original polynomial that you see and split it into 2 parts so that we can set each of those factors equal to 0 and solve. Now, there's other techniques for us to be able to do this, but in the case here where our expression's already factored, it's quite easy to apply the zero product property. Let's look at some more examples. In this case, again, I initially have my 2 factors already given to me. I don't really want to multiply these together using the FOIL method. In fact, recognizing that all I need to do is set each of these factors equal to 0 and solve gets me to a solution fairly quickly. So if I can multiply 2 things together and get 0, again, that allows me to apply this zero product rule. And with a little bit of algebra here, we move our constants to the same side. In this case, I get 4p is equal to -3. When I go to divide, I get my solution, which is, again, some kind of fraction. So by division here, we get p is equal to -3/4. In the second case, we follow the same sort of structure for our algebra, and we get, well, +3/4. And you may be able to recognize this particular problem, again, if I were to actually go through and FOIL, this is actually a product of conjugates. In other words, through the FOIL method, I should get something like 4p times 4p, 4p times -3. If we do the same thing again for the other pair of terms, our middle coefficients cancel each other out, and all I'm really left with is something like 16p squared minus 9 equals to 0. So this is a difference of squares, which is what our product of conjugates always gives us. And so those patterns of recognition for multiplication that I mentioned were important later start becoming really critical to seeing here. So let's look at another example, because we're not always going to be given the factors of our expression. So let's take a look at an example where I actually have to produce the factors first before applying that zero product property. So they give me the first task, which is to set the expression equal to 0. We factor using a variety of techniques, but ultimately we are interested in factoring into those terms a and b so that we can apply the zero product property. Once we've separated our factors, we can apply all of our linear equation rules about those addition, subtraction, multiplication, division properties of equality to solve. Once I get a couple of solutions, I ought to be able to check that they actually work in the original equation as well. So here's an example. I'm asked to solve 25p squared is equal to 49. And we can actually solve this using some other techniques as well. But let's look at how we would do this by factoring. First thing I need to do is set the equation equal to 0. In this case, I can accomplish that by subtraction of 49 from each side of the equation. So now I'm left with 25 p squared minus 49 equals to 0. It may not be obvious, but this is actually a difference of squares. The expression on the left-hand side can be rewritten as a square minus another square. So when I actually think about how do I figure out what are the things that go into this blank here, right? What is it that gets squared to accomplish this setup? Can be a challenge. I encourage you to think about a way to keep handy a list of ways of factoring while you're working these types of problems. So for instance, 25p squared could be written as, in this case, 5p raised to the second power. And of course, 49 is really just 7 squared. Recognizing what the sort of blanks are inside those parentheticals allows me to figure out what the product of conjugates should be. We know that a product or a difference of squares works out to be a product with conjugates. And so this would factor to give me something like 5p minus 7 times 5p plus 7. In this format, I can now take and apply the zero product property. So each of these factors can be set equal to 0 and solve for. So now we say that 5p minus 7 is equal to 0, or my other factor, 5p plus 7, is equal to 0. The linear equations that we have now are pretty easy to solve. Again, we just move our constants to the same side and use the division property. So one of my solutions is p equals 7/5. In the second case, we just get the opposite, p equals to negative 7/5. So again, we should expect that there's two solutions. If we look back at the original equation, it has a degree of 2. And so there we have our positive and negative solution. Let's look at another example together. This one's a little bit more difficult in the sense that if you're not careful, you might think, oh, well, I can just take my two factors here, right, a and b, and say, well, they must be equal to 3x. But remember, the name of the property is the zero product property, not the 3x property. So in fact, I can't initially set these equal to 3x and solve. My task is a little bit more challenging than that. I actually have to multiply these together and then move my terms all to the one side of the equation. In other words, setting this equal to 0 is the first priority. So by distribution, the FOIL method in particular, I get something like 3x times x is 3x squared. 3x times negative 1 is negative 3x. My middle terms here give me minus 8x, and then positive 8. So with it being factored, or rather multiplied out in this manner, let me clean that up just a little. I now see that I have, well, that didn't work out, did it? I now see that I have at least one other term on that left-hand side that needs to be fixed. So when we move 3x to the other side to set this equation equal to 0, we're going to be subtracting. And so I've got quite a few like terms that I need to combine here. So there we go. We have something like 3x squared minus 3x gives me negative 6. And then minus 8 more gives me something like minus 14x plus 8. Now all equal to 0. So this is a trinomial, and it's of the type that I need to use one of our particular techniques called the AC method on. Recognizing the different values for a, b, and c is necessary here. So I have something like a equals 3, b equals negative 14, c is equal to 8 for this problem. So that's the start of the AC method. What we identify are the answer to two questions. We need to find factors of a times c, which in this case gives me 24, that also add together to give me the middle coefficient, negative 14. So what are those values for m and n? Well, it can be a little bit of a challenge here because we have to think about the signs for all of these factors. So what are two numbers that multiply together that add to give me negative 14 but multiply to give me 24? I mentioned previously that the easiest way to answer this question is to think about all the factors of 24 and then figure out from that list which answers the second question. Because they multiply to be positive but add to be negative, it turns out that both of my factors are going to have the same sign, and they're in fact going to both be negative in this case. So in our particular example here, negative 12 and negative 2 are what answer those questions. What do we do with that information? Again, we take the original polynomial that you see on the left-hand side of this equation and split the middle term into those two parts. So here's what we're going to have. 3x squared minus 12x minus 2x plus 8 equals to 0. We factor by grouping now, looking at the first pair and the second pair, we would identify what it is that they have in common and remove it. So for 3x squared and negative 12x, we would remove the common factor of 3x, leaving us with x minus 4. And we should expect that same x minus 4 shows up in the second case. Notice that my signs are going to be wrong because it's negative 2x plus 8 if I try to remove just a positive 2. So in fact, I need to remove a negative value so that my signs are correct here. And again, if I multiply all this stuff back out, it should give me back the original that I started with. Now the binomial x minus 4 is the common GCF, and removing it from each of these terms leaves me with a product here, x minus 4 and 3x minus 2. Those are now what I can use to solve. And I've kind of run out of space here, but we would set each of those expressions equal to 0 and solve. In the first case, the first expression, x minus 4, gets set equal to 0, and we find that x equals positive 4 is one of my solutions. If I take the second factor, 3x minus 2, and set it equal to 0, we find that x equals positive 2/3 is my solution. So this is a more complicated example, but it illustrates the necessity of understanding how to factor and deal with these types of quadratic expressions. Let's take a look at another example. In this case, I start off with a trinomial of some type. However, it's not exactly set equal to 0, which is my first task. To move everything to the other side here, we're going to subtract 12x and we're going to subtract 63 from each side. What that accomplishes is, again, setting my equation equal to 0. So I end up with the trinomial here, 3x squared minus 12x minus 63 equals to 0. So I do have another trinomial here that I could factor using the zero product rule, hopefully. However, in this case, look at the digits. They're quite large. In fact, all of my terms happen to have a GCF that I can remove first that would make this a lot easier. That GCF happens to be 3. So if I remove a 3 from everything, it now becomes x squared minus 4x minus 21 times 3 all equal to 0. I'm interested in solving for x, so it seems as if I were to try to divide each side by 3, it kind of just disappears. And that is quite fortunate because now I'm left with the quote easy version of the sort of AC method, where my coefficient on the square term is equal to 1. So now my task is to identify factors of 21 that add up to negative 4. So again, I would generate a list of factors for 21 and discover that in this case, m equals negative 7, n equals positive 4 would answer those two questions. They multiply to give me negative 21 and should add, in this case, to give me negative 4. I should actually put the right factor here, however. Excuse me, positive 3. With that, I can then split my expression up into its factors, which would be x minus 7, x plus 3. Setting them equal to 0 allows me to get the right answer here. Again, that is applying that zero product rule. So we find x equals positive 7 to be one solution, and x equals negative 3 to be the other. So there we have it. The first task here, again, is to set the equation equal to 0. Finding that GCF helps a lot as well. You could actually work this out the hard way using the AC method, but of course it is a bit more tedious, as you can imagine. Let's look at just a few more examples. Here we're asked to use the function notation to answer some questions regarding these equations and polynomials. So the function notation again uses f of x and states the name of the function that way. Here, for instance, it says for the function f of x equals x squared plus 2x minus 2, find x if the function is equal to 6. In other words, given 6 equals x squared plus 2x minus 2. Solve for x. That's question A here. So how do I do that? Well, again, we need to set the equation equal to 0 and apply all the properties that we've studied so far. Starting in this case means subtraction of 6 from each side, so that I get the equation 0 is equal to x squared plus 2x minus 8. So the question here is now, using the AC method, what are the factors of negative 8 that add up to positive 2? In this case, we would find that x minus 2 and x plus 4 would satisfy the two criteria necessary to factor this expression using the AC method. Negative 2 and positive 4 will multiply to give me negative 8 and also add to be positive 2. With those two factors in mind, we can apply the zero product rule and say, well, x minus 2 equals to 0, or x plus 4 equals to 0. We move our constants to the same side and get our solutions x equals 2 and x equals negative 4. So there we have the answer to part A. In part B, it asks me to find just any 2 points that are on the graph of the function. The best way to remember that this has a x comma y value for the solution is because it asks you for points that lie on the graph. So how do I find points on a graph? We've mentioned before that you can think of this expression here as a sort of black box that I stick numbers into, it performs some computation, and spits out an output value. Well, if we want to find points along the graph, we just stick some numbers into the function and see what comes out. In this case, we already have 2 good numbers to use. We noticed previously that the given equation here actually already was solved, and we identify the x values for which it would give me that value of 0. So the solutions we might use are the ones we already found. When x is 2, we saw that the equation went to 0. We also saw when the x value was negative 4 that the equation is 0. So answering parts A and B actually give us a solution to both questions. Another way that this question might be framed is by asking, what is the 0 of a function? In other words, when does the function equal to 0? In this case, I'm given the expression 3x squared plus 10x minus 8 and asked to find the zeros. So I make a substitution. We want to know, when is this expression going to be 0? By setting it equal to 0, we can apply some of the same methods we've discussed. In this case, again, the AC method makes the most sense. My task would be to identify, again, what are the m and n values that multiply together to give me, in this case, negative 24, but also add together to give me positive 10. So again, I would consider a long list of factors for 24 and then consider what should the signs be that make this work. Since they need to multiply to be negative, they're going to have opposite signs. So I would use, in this case, m equals positive 12, n equals negative 2. Those will add to be 10, but multiply to be negative 24. So I can then factor this by grouping. I've got to take and split that middle expression into 2 parts, however. So we would take positive 10x and split it up into 3x squared plus 12x, negative 2x minus 8, like this. Looking at the first pair, we have 3x as their common GCF, leaving me with x plus 4 as the binomial. In the second pair, they have negative 2 as their GCF, again leaving me with x plus 4 as the binomial. The last little step here is, again, to factor out the GCF, our binomial, and multiply by the sum of the remaining factors. Applying the zero product rule leaves me with my 2 solutions here. We get x plus 4 equals to 0, or 3x minus 2 is equal to 0. And one of my solutions is just x equals negative 4, the other positive 2/3. So Asking for the zeros of the function is not much different than asking to solve for one of these quadratic functions. The naming nomenclature and methods, generally speaking, are the same. Let's look at just a few more examples. In this case, I'm asked to find the zeros of the function, which we've already done. This is the exact same equation, 3x squared plus 10x minus 8. So going back here real quick, the functions we found were x equals -4 and x equals 2/3. So when this function is equal to 0, right, that tells me where this crosses the y-axis. So when they ask me in parts B and C, what are the x-intercepts and what are the y-intercepts? I don't actually have to know what this thing looks like in order to be able to answer that question. So remember that the x-intercept always has a y component of 0, which means our x-intercepts were what we just found. When x is equal to -4, we said the function goes to 0. When x is equal to 2/3, again, the function goes to 0. So these are the 2 points that would reveal the x-intercept. For the y-intercept, it's just where x is equal to 0. So if we plug in x equals 0 and solve, we'll find our other point. Given the function here, I want to find when x is 0. So by substitution here, I just plug in that value anywhere I see the variable. So 0 squared times 3 is still 0. 10 times 0 is still 0, which means that the function evaluated at x equals 0 is going to spit out -8. If I want to give a point, which is what this is asking for, I would say, well, x is 0, y is -8. So here are answers for part B, and here is the solution for part C. So one last application I want to show you is an instance where we look at a geometric figure and ask similar type questions. So here I'm giving you a figure, a rectangle, that tells me the area in square feet, 117. The length is described here as being 4 feet more than the width. And so they've given me the figure with those connections in mind. And they just asked me to find what is the length and the width for this particular value. So in this case, we need to know things like what is the description of the area and how does it relate to the sort of geometry of this figure. Well, it's length times the width, where this expression is what gives me the length. And so we could say that the product of the length, which in this case is a binomial, w plus 4, times the width, which is just w, is equal to 117. When we multiply those together, we ought to get the solution here. So for our purposes, we can do the distribution here and try to solve. We multiply and get w squared plus 4w. And by moving this term to the other side, we end up with our quadratic. So how do I solve this quadratic? I need to know things like what is the product of two numbers that multiply to give me 117 that add together to give me +4. So in this case, it's a little bit more challenging. So I don't know about you, but I don't exactly know the values of 117 that would, give me that solution. So it may take a moment here. When we think about how to factor something, we would look at things like, what are the values that make this number up? I know, for instance, that 117 is divisible by 3. So I could use, a little bit of prime factorization here to arrive at that value. Something else that's helpful here is to think about the fact that they need to add up to be a specific number. So they're probably going to be close to the same value. So by factoring a little bit, I can see that, for instance, 3 times 3, which is 9, would multiply by 13 to give me back 117. If I give them the proper signs, I can have them actually add up to be positive 4. If we make 9 negative and we keep 13 as positive, we'll be able to solve for our two factors. So we're left here with something like 0 is equal to w minus 9 times w plus 13. And my dog Holly's very upset that it's taken so long for me to solve this. So real quickly here, we find that w and the two solutions we're going to have are by setting these factors equal to 0 must be equal to 9 and negative 13. However, if you'll think about it, one of these factors being negative doesn't make any sense in the context of an actual figure. So it really could only be the case that w equals the positive value, 9. If we add that to our other expression here, we get L must be equal to then 13. So there's our two solutions. So there's some geometry aspects of this that we could come across on occasion, but that about sums it up. Sounds like I've got a dog to go take care of, so I'm going to end it here. We'll see you all next time.